In this video we're going to take a look at Phase 2 of the Hacky Holidays Space Race powered by Hackazon and run by Deloitte. So this is a 3-week competition. We went through the Phase 1 challenges in the previous video, most of them anyway, and we're on to Phase 2 now, so you can see quite a few of the challenges solved here. I'm just going to go through and record a few and we'll see how many we get done. The first challenge is called Power Snacks. Let's take a look at that. So the description says, are you the very best PowerShell user? Try this challenge to get better acquainted with PowerShell's functionality. You need to come up with some commands that result in a specific output. You can check your output by piping the result to the check function. For example, get contents, words, do something, check, so you can see it's been piped through there. And it says, do not use any format function before piping to the check function. Also note that the checker may not understand all sorts of inputs. Try piping your output to the outstring function first, to make sure your output matches more closely the given example. Lastly, instead of write host, use write output to be able to write to the checker. Alright, so we've got a system that we need to launch here, which will give us a terminal, a PowerShell terminal to go and run these challenges against. We've got 4 parts, and the first part says, write a script that writes out all numbers, 1 per line, from 1 to 1337, inclusive. However, if the number is divisible by 42, instead print the string life, the universe, and everything. So let's try and do that. I'm going to create a new PowerShell file here in Codium, just so we got some syntax highlighting. And I'm going to copy over my first solution here. So we were told that we needed to send this to the check function. Let's see what happens if we don't send it to the check function. So let's just grab this loop, and here we're just looping from 1 to 1337. And if the number is divisible by 42, we print life, the universe, and everything. Otherwise, we'll print the number. Let's go to the system that it's launched for us. So yeah, we've got a terminal here, a PowerShell terminal. Let me zoom in a bit, and let's paste this loop in. Oh, it doesn't have the loop copied. Paste that loop in, hit enter, it all looks good, but if we try and, well, it didn't give us a flag there anyway. If we try and just send this, let's do check. Yeah, let me copy the whole thing here. So we're basically just saving the result of that loop to answer. Let me do that first actually. We can just send this all as one command, and now we can then send answer to check, and that gets our first solution. Or yeah, we can just send that whole thing, and that gets us the first flag. Let's have a look at the second part of the challenge, which says you're playing Scrabble with your friends. You have the letters I, Y, D, H, L, A, O. What are the words that you can form? Sort them by increasing size, then alphabetically. Only include words of 2 letters or more. Make use of the dictionary file dictionary in the work directory. An example excerpt is given below with different letters. So assuming that you had some letters here, then you need to find some dictionary words. So let's have a look at the script that I have to solve this. So go back over to Power. Let me zoom in on this a bit as well. So we have our script here, and this time we're just looping through, so we get the contents of the dictionary. We're going to sort them by length and then alphabetically as well. And for each word then in the dictionary, we're going to make sure it's at least 2 characters, and if it is, we're going to basically loop through the characters in the word and make sure that we have enough characters here to create the word. So if there are any characters in this dictionary word which aren't in here, then we'll not print out the word basically. So we also need to make sure that if we use a character, that we remove it from the characters that we have left. And we're just using this match variable then to determine whether or not we were able to recreate the word. So we could, let me do this first of all to answer, just so we can have a look at it. I keep going to the wrong terminal. And let's just have a look at our answer first then. So you can see that it's printed out from the characters that we had there, it's selected these words from the dictionary. And let's send our answer through to check as well. And you'll see that we get our second flag. Let's go back and have a look at the third part of the challenge. And this time we have passwords.tsv, so we have this these tab separated values, and you get an overview of often used passwords. Can you give us an overview of the number of passwords per category? Sort them in by descending count. Example excerpt given below. So again, I'm just going to grab the script that I used to solve this, and let me turn on word wrap here. So we are importing CSV. Let me just do this first of all actually in the terminal. So if we import this, then we can see that each item has a few different fields: a password, a size, a category, a rank. At the moment we're being asked to find out the number of passwords per category by descending count. So if we go back to our script here, we're importing this and then we're grouping by category, and then we're sorting by count, descending, and then we're basically just grabbing the count and the name. So let's run that and see what it looks like. Try and print answer, and you can see here that looks similar to what they have, and they have nerdy 30, animal 19, which looks good. So let's try and do answer check, and we get our third flag. So the final part of this challenge is called names. It says, given the passwords file, supply a list of passwords from the names category ordered first by ascending password length and then alphabetically, and here's an example below. So again, I'm going to copy over the script that we have here, and we're just importing the passwords.tsv. Again, this time we're going to sort by password length and then alphabetically by password, I believe. Yep, and then where the object category is equal to names, we're going to select the password. So let's just go and test this out as well. Print the answer, and it's all looking good. It's in order of length and then alphabetically. Let's test it out, and then we get our fourth flag. The next challenge is called injection traffic. It's a network challenge, and the description says, help us run forensics on this database exploit. We've got one part to the challenge which says, we observed malicious traffic towards our database server originating from the web server. Can you find out the sensitive piece of information that was stolen? And then we have our flag format. It's going to be CTF with a 32 hex value in the middle. So we have a PCAP here. I'm going to wget that. And let's take a look at it in Wireshark. You can see I have some columns here which aren't all the normal columns. This is the USB data, which we don't have any in this case, so I'm just going to remove it to make this a little bit cleaner. And let's adjust the output a little bit. Let's have a look at a little bit about the file. So it was a 34-second attack by the sounds of it against the database. We've got 3,500 packets. Let's have a look at what type of protocols we're dealing with. And we can see here we have this tabular data stream, malformed packets. So can we select that and see are these of interest? You can see that we have some responses here. There's some mentions of database queries by the looks of it. You can see some unions and selects. Alright, let's remove that filter and just have a look through. So you can see we have our SQL batch here in the info where we're selecting all from articles, and then we have a response with this lorem ipsum in it. We send another SQL batch, we have another response, another SQL batch, another response. Notice that the response sizes are different, so we're either getting a 165 or a 200 response. So we might want to try and drill through some of this data, go and have a look through it in Wireshark. We can also extract some of this data using T-Shark or something if we want to have a look at it in a text file. So let's have a look at that. So we might want to run here T-Shark-R traffic to read in the traffic PCAP, and then we'll extract some fields. So we'll do T fields, and the fields we want to extract, we could extract this tabular data stream query. So I'm going to do tds.query, and you can see then we're printing out these different SQL statements just so that we can go and try and analyze this a little bit better. So let me actually send this to sqli.txt. We could open that up, and it just means we can go through and have a look at the different commands that are in here, if we go through, we can see that basically it's running a blind SQL injection attack. So we can see here this is going for the fourth character. It's checking, is the fourth character, is the value of that character in decimal greater than 112, and based on the response that comes back, it'll determine whether to either lower or increase the value, and it'll keep doing that until it finds out what is the correct value for the fourth character, and then it'll move on to the fifth character, etc. If we have a look through here, there is some different syntaxes, so this is important. Obviously we have a few different attacks which are being run against the server. Maybe this was a automated tool which is just trying some different blind SQL injection attacks, but essentially we need to go and try and automate a process to try and decode what these correct values actually are. Let me see if I can just find an example. One thing to note, by the way, what I did here, if we look for 1, 1, so let me search for whole words 1, 1. So we can see here on the right how many attacks there are based on how many times they try to identify the value at 1, 1. So the last attack which occurs is right here, and this is actually the only attack which goes up to enough characters. So if we go down to the bottom, you can see it's going up to 37 to 38, and we know that we need CTF, curly braces, and then a 32 hex value in the middle. So this would actually be the only one which would possibly give us a flag. And just to show a bit clearer what's happening here, so for example the 37th character, it's having a look to see, is it greater than 125? It's come back then to say, is it greater than 123, because obviously that's come back false. So then it's coming back with 124, and that's where it eventually finds, yep, that's the correct value. We can now move on to 38. So if we go and take that 124, let's go to, you can go to CyberChef or something like that, or just put this into Python. But if we go and convert that from decimal and see what that value equals, it actually equals a pipe symbol. But if we increment it by 1, that's our second curly brace. So we could go and do this manually. We could go and start off at 1, 1 here, and let me go back to that 1, 1. So we could go back to the 1, 1 here. It's got 67. Let's try and put in the decimal value. 67. We've got a C, so that's looking good. So the next one's going to be a T, and then F, and that's going to be our flag. But we don't want to sit and manually go through all this. Let's see if we can automate the process. So if we analyze the PCAP a little closer anyway, we would find that essentially what's happening here with the 200 responses is if the condition comes back true, it's 200. If it comes back false, it's a 165. So I wrote a script to extract some of this data. Let's take a look at it. Exploit.py. Let's paste this in here. And essentially what we have here, we're just loading the PCAP. We have a fake flag initially because we know we're going to need to fill this up, and it's going to loop through every packet in the capture. It's going to extract the query as we just did there as well. It's going to make sure that the substring, because there's some different attacks in there and some other queries, just want to make sure it's only looking for the SQLI attacks, and it'll go through each one of those. If the next packet after that SQLI packet is a 200, so if the response is a 200, then we know that that character, it's going to be greater than or less than that character or whatever. So we'll basically just update the character. We'll extract the use regex to extract the index. This is the index of the character in the flag, and then we're also extracting the value, which will be, let me just go back here. So we're extracting here the 2 or the 1, which is our index, and then we're extracting this value 66 or 67, and each time it comes back true, we're updating that value, and it'll basically just keep going through that process, because we know that there's a few different attacks in here, right? So it's going to go through each attack at the beginning, and they're not going to actually get back flags, so we want to keep overwriting until we get to the very end, and that's basically it. It's just going to print out the flag once it's done. So let's try and run it and see what happens. just need to install PyShark. I might need to install it from GitHub, I'm not too sure. No, it looks okay. Alright, let's try it. Okay, so it took maybe 30 seconds to run and it came back with our flag, and then that's it. Just take a copy of that and paste that in, and we've done the injection challenge. The next challenge is called Unidentified Graphics Object. It's a Stego challenge, and the description says, we've seen an unidentified graphic object for advertising a new spaceship. It was created with one of the universe's most advanced design tools and can store information alongside the image in different dimensions. And there's two parts to the challenge. The first part says, the agency who created the spaceship has included some subliminal advertising. Can you find out what their secret message is? Flag in CTF hex. So I actually solved the second part by mistake first, as probably a lot of people did, but let's go through it in the correct order. So we have this file to download, an APNG file. Let's download that. And we can just run a couple of basic checks. Let's see what the file type shows. It shows it's PNG image. We could have a look at the EXIF data. And one of the first things I always do with any PNG image is run zsteg. So we can run zsteg with all checks. And it'll just try to look at different bit planes and things like that, and different Stego techniques, and try to extract data. In this case, we don't actually find anything. Let's go and have a look at the image. So we have this image. We can zoom in quite a lot on it. We can move that around, but nothing particularly of interest by the looks of it there. It's a very big image, 64 megabytes for a PNG image, which doesn't really look to be too interesting. We could try and open this in, let's try something like Stego Suite. Not Stego Suite. Steg solve. We can open it there, and I won't actually open it at the moment. Alright, so let's go and have a look at what this APNG is. Let's Google APNG file, and we'll find that it's an animated portable network graphics file. So let's see if we've got any tools that we can use to deal with this. So we might want to run something like sudo apt cache search APNG and find some different tools that we could potentially use here. So we have one to assemble APNGs. We can convert APNGs to GIF format. We can disassemble, deconstruct. So that sounds pretty good. Let's try and install that. I might still have it installed here. I revert my snapshots a lot, so it's hard to tell. Alright, we've still got it installed. Let's try and run it then. APNG dis and UGO. Oh, what I'm going to do first actually is create a new directory called frames. I'm going to move that into frames because I know this is going to create a lot of files. And let's try it now. APNG dis. And this is going to disassemble all the frames. Let's go and see what it's actually doing. It takes quite a while. Okay, so I sped up that process. It does take a couple of minutes to run, but now we'll have 60 or 61 different frames, and then also a text image with all of them. So let's have a look at the text images. The text files first of all. Each one of those has a delay in it, most with 95/1000. We have some other values here as well. So this is to do with the second part of the challenge, so I'm going to leave that for the moment. Let's go and have a look. The second part of the challenge was a lot easier to solve. If we have a look here at the images now, at the frames, we can start to go through them, and it's basically just an animated image. So I spent quite a long time trying to do things here, so in terms of maybe doing a difference. In fact, let's just do that as an example. So we could do something like, I tried to extract the alpha, for example, because if we do like PNG check UGO, no, if we do PNG info, oh yeah, well we can see there RGB plus alpha. No, not PNG info. Okay, we can extract the alpha, but the alpha is basically just all white. We can try to make a composite. So let's do composite, and we can do all.png, which will take all of those frames, and then we'll compose the difference to difference.png, and that'll get the difference between all of those frames. Maybe there'll be a flag somewhere, but there wasn't anyway. There was nothing of interest here. So eventually what actually happened is I found it by accident when I was using Steg solve. So let's open up Steg solve again. Let's open. I basically went and selected one of the images here, and I just happened to select image 60, which if we go and have a look at the ship on it, you can actually see a flag right here. I don't know how well you'll be able to see that at the moment, but it just so happened that I'd opened this image and saw the flag there. But if we go and try to open that up here and zoom in, it's actually quite hard to read the full flag. So we can see 4D11, 5CB1C83, that looks like, CACEC maybe, and then maybe 3 E's here. So some of them were kind of hard to work out, and it took a while to brute force them. Actually, I spent quite a long time trying to sharpen the image and get rid of the blur and do different things, which did help a little bit, but I tried maybe 30 flags before I got the correct combination of hex values. But that's how we solved the first part of the challenge anyway. Well, that's how I solved it. Let's go and have a look at the second part of the challenge. The description to this says, this new image format also features space-time support to embed information using time into the 4-dimensional manifold. So this was the kind of easier bit, using the text files. Let's go and cat all the text files to delays.txt. Let's open that up. And we have our delays in here. So these ones don't look of interest, they're just repeating a lot. So let's remove all of those, replace those with nothing, and let's also remove any mention of delay, and let's also remove this /1000, and then we're just left with some decimal values here. We've got a lot of new lines as well. I'm not used to, I'll never get used to Sublime. Let me undo that. Let me replace new line with a space. There we go, that'll do. I'm just going to grab these decimal values. I'm going to go to CyberChef. I'm going to paste this in here, and then we're going to say from decimal, and there we get back subliminal space-time messages. Subliminal, it looks like it's not actually got the flag completely correctly there, but it did. Maybe I've removed something that I wasn't supposed to remove. Oh, there we go, subliminal space-time messages. There we go. Okay, so it was just the new lines in there. The next challenge is called Scorching, and it's a Redteam challenge. The description says, Windows domains are hot, scorching even. Note, a domain controller is spun up on demand. It may take a while to fully boot and launch. Verify whether it's online by checking port 445 on this IP. So I've already launched the server there just because it mentioned it takes a little while. And we've also been given this hash.txt file to take a look at. So the first part of the challenge is called password. It says, can you find out the password for the hash in the file? It is for the N account user. Hint, the password does not meet the password complexity policy as it is less than 8 characters and it only includes letters and numbers. Alright, cool. So let's download the hash first of all. Let's have a look at it. Alright, so we've got this NTLM hash to crack. Okay, so I've jumped over to the Windows system here. You can see we've got the hash in the hashes.txt file. It's just a lot quicker to run hashcat with the graphics card. And if we want to run then hashcat.exe on mode 1000 for the NTLM hash, we're going to pass in that hashes.txt, and then typically what I would do here is pass in a word list. So word list, for example, crack station real is a big word list, and that'll loop through. We can check the status as it's going through. There we go, it's quite quick. You can see there 37%, but that's not going to crack the password for us, and we were told specifically that this is less than 8 characters. So what we're better off doing here is using some rules. Let me run this again, but instead of passing in a word list, I'm going to set this to -A3, and then the rule that I'm going to pass in, we can essentially say here how many characters we want. Now if you know it's up to 8 characters, you might need to go through and actually, well, start at 7 and then go to 6 and then go to 5, or vice versa, because Hashcat, from what I can find, doesn't seem to have an option to just use a variable length in this rule format. But if we run this anyway, it just so happened that the password was 7 characters long, and you see that's actually going to take quite a while to crack. Let me leave this to continue. Okay, so it took around 7 minutes, as you can see here, and it found the password Hacky21. So we would take a copy of that, and then that's going to be our first flag. So moving on to part 2 of the challenge, the title is Scorching, and the description says, can you find out the flag hidden in the shared directory for the S account user? Hint, the password is part of rocku.txt. So this time we actually need to go and take a look at this system which is set up, which we didn't have to do in the first part of the challenge. So I need to connect the OpenVPN, which I have here in the downloads, and that means we'll be able to go and run an nmap scan. So I'm just going to run a scan, enumerating services, running the default scripts, and 10.6.0.2. Note that I didn't run the nmap scan against all ports. We just checked the top 1000, which is all we need here. And we see we've got quite a few open, so we can see the DNS, SSH, we've got our LDAP, we have our RDP, remote desktop, and I did try a few different services here. I mean, obviously we could try to brute force some of those, but we've been told that the password is in the rocku.txt, which would be a lot of passwords to go through if you're trying to brute force the RDP or trying to brute force the SMB. So what we could do is have a look here. Let's run, let me open another tab just in case we want to come back and check these nmap results. But we could run SMB client, and we have the N accounts details. So let's try and run 10.6.0.2. and it's asking us for the password, which is Hacky21, and you can see then we're able to list some of the shares, but the issue is if we try to get into these, most of them aren't available. The only one we'll be able to actually list files, I believe, is the sysvol. Let me double check that. So yeah, we can, and then we can see this insecure AD local, and we do have some things in here. So I did go through and download some of these things, but they're not going to be of much use to us. Let's see what else we have here. If we try to even connect with evil WinRM to the N account, let's do 10.6.0.2 user N account, and then the password Hacky21. We don't actually get a shell on this account. Something else I tried as well is running crackmap exec. So if we try to brute force the SMB, I mean really we shouldn't be brute forcing. Let me just grab a copy of this to demonstrate though. If we try and run Hydra and try to crack the S account with the rocku.txt on SMB, let's see how quickly this goes through. You see our evil WinRM didn't manage to get a connection. I'm going to wait till that starts going, but we'll compare that to crackmap.exec, which if we set that to the SMB protocol 10.6.0.2 and then the user S account and then set the password to user share wordless rocku. Let's just compare this. I think this is still just trying to even compile the word list at the moment, but this will run through very, very slowly if it starts. Let's just see how crackmap.exec works. I can't even speak. So you can see how quickly that's attempting passwords. But obviously this isn't the solution for us anyway, but it's just worth bearing in mind if you're trying to brute force a protocol, check out crackmap.exec rather than the Hydra or something else. So you can see here, okay, 202 tries per minute. Maybe it's just not printing as it's going, maybe the other one. Be interesting to compare the speeds of those, but I think the crackmap.exec is a lot quicker. So at this point, maybe after trying a bit more enumeration, I went back to the nmap scan, and a big hint is the domain name here, insecuread.local, so insecure active directory. So if we're going to have a look at some active directory enumeration exploitation techniques here, we'll find that we've already used some of things. We've already tried to enumerate the SMB. We have done our nmap scan. We've tried crackmap.exec with the SMB. We could use this Kerberos enum users module of Metasploit, although we've already got the username. We're trying to get the password. But look at the mentions here of roast as well. We have roast here. We have Kerberos as well. And the name of the challenge is Scorching. So scorch is another word for roast. And we can see here that we have some scripts which are part of inpacket which we can try, like this getAdUsers.py, which I did actually try this one didn't work for me. Let's go to the actual Kerberos section here. You can see here, find more information on the Kerberos page, and here we actually have then this getUserSPNs.py as well, which says you need valid credentials inside the domain, and we do have valid credentials. So if we try to use this script, we should be able to make this request with the IP address, the domain name, the username, and or we could use the hash. We don't even need to actually crack the hash that we were given, but let's try that out. So let me locate getUserSPNs.py. You can see I have this in inpacket, so we'll run Python, and then we need to provide request DC IP, and the IP is 10.6.0.2, the domain, which is insecuread.local, and then the account, which is n account, and then we want to output this, so output file hashes.kerberos. So we can go and double check what we've just put in there. We've put in our domain, we've put in the username, and then we're outputting that. So it's just the exact same command that we have here, and a password will be prompted. So if we try and run that now, we'll be asked for our password, which is Hacky21. We'll enter that in, and now let's have a look at our hashes. So you see we've actually produced a hash now that we'll be able to go and try to crack. So we're going to run John, and then we'll pass in the format as KRB5TGS. The word list is rocku, so user share word list rocku. And then we'll just pass in the hashes. It cracked the hash, which was MySpace123. And if we go back to our challenge description, it said find the flag hidden in the shared directory for the S account user. So we did our SMB listing earlier. There was some different shares, but this space race one sounds interesting. So let's try and connect to that. We'll use SMB client and then 10.6.0.2 space race for the user S accounts, and then MySpace123 as a password. In here we have this flag.txt, so let's try and get that. Let's print it out, and you can see that we've got our second flag. The next challenge is called Packed. It's a reversing challenge, and the description says, all our operations require optimal space usage. There's not much space in space, you know. Oh snap. And then the next part of the description says, we extracted this information from one of our databases. I guess they did some optimizations to save on space. So let's download this packed.bin file and take a look at it. And you can see here that we can see some text, some of the characters aren't displaying properly, which includes our flag. What we might want to do is just try and find out what does this text come from. So you could try and find some text here which isn't in any way not obfuscated, corrupted or compressed, and see where this is coming from. So this is a Monty Python quote. So you might want to go in there and then get the full quote, and that means you can actually compare it. And this is what I did initially. I went and grabbed the full quote, converted it to binary, and then converted this to binary as well, and then just went to try and kind of work it out in CyberChef, but wasn't getting very far with that. So if we try and Google, based on the hint that we were given here, we can see it mentions snap. And if we kind of Google like snap, well, I think I just Googled snap compression, and you find this snappy compression, which you can go and look into, and it's basically a compression type. So how can we decompress it? Well, let's have a look. Snappy decompress, and you'll probably find some different tools. I'm not too sure which one I actually used. Let me grab the link of the one I used. So I found this link with a tool that was already compiled to download. So you can see we've got some options to import it as a library or to compile it, but we can just download this snappy tool and then run the snappy tool against the value that we want to decompress. So let's take a look at that. Get that, we've got the file then, the snappy tool. Let's move it to a snappier name and then make it executable. Try and just pass the packed binary, I guess, the packed data. In file and out file. Okay, so decompressed. And then let's see if we can print that out. And then we've got our full text decompressed, and at the bottom we have our flag, which is Shimmering Supreme Elderberries. The next challenge is called Cute Invoice. It's a crypto challenge, and the description says, who knew invoices could be cute? So we've got a PDF and a PNG file to download, and we've got another description here which says, who knew invoices could be secure and cute? Our third-party contractor for space shuttle parts is using the best tooling for sending us secure invoices. So let's download the files to begin with. Grab that PDF and let's grab the PNG as well. Download those to the desktop, and alright, so let's just go and take a look at the files. We've got this PDF. If we try to open that, it asks us for a password. Let's just try password. Alright, just gonna keep asking us. Let's so we might want to use something like PDF crack to crack that, pass it in a word list or something, but let's take a look at this image first of all. And this is invoice.png, and we can see here we've got this QT-pass. QT-pass is GUI for pass, the standard Unix password manager, and we have a password then. Password for invoice PDFs here. Password is being generated. It's 16 characters long. It's using the all characters character set. So, based on the screenshot, we probably wouldn't want to use PDF crack with a word list, or even try to brute force it, because there's 16 characters and it's using all characters, presumably all uppercase, lowercase, and numbers and special characters as well. So that's not going to be ideal. But we can see here specifically that the Qt-Pass version 1.2.0 is mentioned. So let's go and see if we can have a look at that release. So I'm going to go to GitHub. What we're going to do is go to the version 1.2.1 release, because we know this is the upgrade after 1.2.0. And we'll see here that then there were some fixes. So there was insecure password generation. There's two issues linked here, and then there was also version 1.2.0 leaks passwords. So if we go and start to have a look through some of these, let's check this. Insecure password generation. It says the current way of generating passwords is insecure. All passwords that have been generated with Qt-Pass in the past must be regenerated and changed. Here is the current password generation function. And what it says here is the problem is the modulo will not uniformly distribute the set. The proper way to do things is just throw away the values if they're out of bounds. You could try to do the calculation correctly to uniformly stretch or compress, but it's hard to get it right, so it's best just to discard the numbers outside and the set and then try again. Second, and more critically, here is implementation of the util rand, and essentially what it's telling us here with the util rand, unfortunately using a non-cryptographically secure random number generator like libc's rand is problematic. It talks about the time issues, but the issue here not only is the current time a guessable and brute forceable parameter, but the documentation for QTime actually indicates that this is merely the millisecond part, so 0 to 999, which means there are only 1,000 possibilities of generated sequence of passwords. This is as bad as it gets in terms of password manager password generation, and suggests some fixes here. So let's go and see if we can take what's been described here and use that to crack this password. To do that, I'm just going to copy over the script that I used then to solve this. So let's create codium exploit.py. Let's paste this in here, and I'll just talk through the script a little bit. So we have this, let's go and check this link out. This is just the, if we go and have a look at the actual code base here, you'll see, let's go into the source, you'll see we have this password configuration, which tells us the character set that's used, which is why I've just linked that there. So that's the character set that will be used, so we've specified this here. The password length is 16 because we know that the screenshot has 16 characters, and we're looping 1 to 1,000 because of the millisecond thing that we just learnt about. And in terms of rand, let's go and have a look at the rand function. We can see that the rand function has a single value as a state, which is modified by a transition algorithm on each advance, like x is modified in the following piece of code. So x equals, so we have this initial value, and then that's gonna basically repeat, so we continue getting these new states. So let's go to our code again. So that's exactly what we've done here, right? So we're looping through, state is equal to, and then it's going to do this on each iteration. So we're basically going to loop through each time. We're going to loop through 1,000 possible passwords, and we're going to build up the password here. So we're going to go through the password length, so 1 to 16, and we're going to basically generate from this character set what the possibilities are. There's only 1,000 possibilities, so we'll then try to open the PDF with the password that's been generated, and if it's correct, we'll print the password. If it's not correct, then we'll just continue. So it's only going to be up to 1,000 attempts anyway. Right here, the actual code that we're using, let's just added a comment there just to show that this is exactly what we have here in the, let's go back into the issue. So right here, this code, this loop, so it's looping through from 0 to the length of the password, which is what we're doing right here, and then it's setting the index is equal to, and we're just doing the rand here, and then next char is equal to the index, and then just add on the password character. So alright, enough explanation, let's test it out. Let's run Python exploit. Oh, I didn't save it. Python exploit. So running through, just going to print out the incorrect passwords. and then eventually we get the correct password, which, yeah, it wouldn't have been easy to brute force this without knowing the vulnerable algorithm. You can see I've just printed out there. I was going to try to parse out the flag from the PDF, but who cares? Let's just open it up and paste in the password, unlock the document, and then there we have our flag. The next challenge is called Engine Control. It's a pwn challenge, and the description says, these space engines are super powerful. Note, the PI file is merely used as a wrapper around the binary. We did not put any vulnerabilities in the wrapper, at least not on purpose. The binary is intentionally not provided, but here are some properties. So we're given the source code for the binary and then the wrapper as well. Let's download those first of all. That's our wrapper, and then let's get the source code. And we're going to need to compile this ourselves and make sure it matches the same security settings that we have here for the binary. So to do that, first of all, we need to launch a server for whenever we're testing this remotely. I'll launch that now. And let's have a look at the first part of our challenge. Says, environmental disaster. These new space engines don't have any regard for their environment. Hopefully you can find something useful. So let's deal with this binary compilation first of all. If we just try to compile this normally with gcc engine.c, and then we'll output it to engine. If we try to run that, then let's do checksec, pass in the file engine, and it'll tell us then we've got the architecture correct, that's all good, AMD 64, little endian. We've got partial railroad, that matches, but we have no canary in our binary, whereas they have a canary, and we have NX enabled, which is good, but we have Pi enabled. So we need to just change slightly just so that we're matching the same binary they're using on the remote server. So we want to disable Pi, so I'm going to add a flag here saying no Pi, and we want to add the stack protector. So I'm going to add here F stack protector. I'm so used to doing F no stack protector. F stack protector, let's try and run it again and run checksec. And this time we've got no Pi and we have the canaries. So looking at that, the architecture we have here, everything's matching what we have on the server side. And just to verify then, the flags that we have here, no Pi means that every time the binary loads, it's going to load at the same base address in memory. It's not going to change each time. NX enabled means that if we are able to inject code onto the stack, it's going to be basically marked as no execute. So data on the stack is either treated as code or data, so it won't allow us to execute that basically. And stack canary is found, meaning if there was a buffer overflow here and we were able to exploit it, we would have to take care of making sure we don't overwrite the canary with an invalid value, which would cause the program to crash. And then the partial railroad is just to do with the read and write protections around the global offset table and stuff like that. So with some of that out of the way, let's take a look at the code as well. Engine.c. So let's zoom in a little bit. So we've a pretty short file here. We've got a main method. It is defining this buffer of 200 bytes, 200 chars, and then we're calling setBuff. We're going to print out asking for a command, and then essentially it's just going to loop through here, taking input offers with fgets, and then it's going to make sure that whatever input we've provided is greater than 0. If it is, it'll print this running command. It's going to print f with the I value which we're providing, and then it's just basically going to keep looping through in that fashion. So let's let me just open up the wrapper quickly as well. So they said there was no intentional vulnerabilities in this. Essentially it looks like this is basically just setting up the communication for the process. We'll go back to that later. For now, let's see what kind of exploits we can do here. So we know there's no easily exploitable buffer overflow here, right? Because we have stack canaries and the bounds are being checked here as well. But what we can do, let me make the file executable first of all. Let's try and run it and see what happens. So we'll run engine. It asks us for a command. Let's try and put in a command, and it's just saying, alright, it's running a command, but we're not getting any output back. That's all we can really do. We can exit the program. We could try and enter in a lot of characters. So we have, the buffer was 200, right? Let's try and enter in a lot of characters. and you can see then it doesn't cause any segmentation fault. It's just basically repeating the overflowed characters in as the next command, so no buffer overflow there. So what is the vulnerability? Well, this printf call here is taking the user input and it's not specifying what format that should be interpreted as. So it's not saying that it's a string, it's not saying it's a decimal, and it's allowing us to potentially inject a format specifier in here. So let's just open up quickly C format specifiers. You can see some different examples of specifiers here, so we can say that we want to represent the data as a character or as a decimal or unsigned integer. We can, this wasn't the kind of reference guide I was really looking for, 1 second. Okay, so we can use X for hexadecimal, we can use string for a string of characters, we can use P for a pointer address. So if we go back and we've still got the program running here, what if we try and enter in %x? Alright, you see that? So if we do that twice, we're actually getting, we'll get multiple values. So let's do, I'm separating them as a space just so that we can see it a little bit easier, but it's not necessary. And essentially what this is doing is reading 5 items off the stack as and interpreting them as hexadecimal values. We could go ahead and change that to a pointer. Let's try that. And again, then we can see the actual addresses. So it looks like we have these are addresses that we might want to leak to try and identify the offsets of things. So the offsets of functions in the program or in libc, etc. Note that we had the %s specifier as well, which would print as a string. Let's try that. Now you'll see in this case that came back okay. Let's try that again. I'm going to try it with a few more values, and you'll see we've got a segmentation fault this time. So the string format specifier is not actually trying to interpret the value on the stack as a string. It's trying to, it's interpreting that as a pointer. So it's going to go to whatever address is on the stack and then interpret the value at that pointed to at that address with as a string. In this case, we've basically put in a few values there, and it's tried to interpret one of these values as a memory address and cause a segmentation fault because it can't do that. So if we wanted to actually view something as a string, what we'd probably need to do here, let me try and run that again, we could do, let's do some of the pointers again. So we could do some of these pointer values, these are giving us the hex values here, and then we could actually take these hex values and go to convert them to ASCII. We could go to CyberChef or something like that, and it's not necessarily going to be something which is represented as a string, but in this case you can see that this is actually the format specifiers that we've been providing, which are on the stack, and we've leaked those and then converted them into a different format. So one thing to bear in mind is it can get a little bit tedious printing out all of these values in a row. So if we wanted to leak hundreds of values off the stack and we had to provide these all, not only is it going to be a lot to type out or to keep track of when copy and pasting, but also the buffer might be small. So we've got 200 bytes in this case, but what if we want to read 500 pointers off the stack? We're not going to have enough space to do that. So what we can do in those circumstances is use a slightly different format. So if we use the percentage and then a value, let's say 35, so we're going to read the 35th element off the stack, and then we're going to interpret it as, in this case, a pointer, but we could interpret it as whatever we want it to. Let's try that again with a different value, let's say 50 and $P. You can see we've grabbed a value here, so if we were running this in GDB, we could go and have a look and see what does this value currently point to. Is it a libc function? And then can we find the offset to other libc functions from there, like system and like the bin.sh string, for example. Alright, so we've had a look at the vulnerability. Let's put together a script to see if we can do a bit of fuzzing and see exactly what values might be worth leaking off the stack. So to save on time, I'm going to copy over a script which I've already prepared. Let's open this up as fuzz.py, and if you looked at the last video or you've been through any of my pwn videos in the past, this is just a template which I use to make it easy to swap between GDB and local and remote execution, and to set up GDB scripts if need be. And then here we're just defining whether we want to print out a lot of logs or not, a lot of login information, and setting the binary and the context binary so that later on in the script we don't need to worry about what architecture bits and operating system it is. It makes the script quite portable and reusable. The only bit we're really interested in here is this exploit goes here bit. So I'm going to take a little bit of this out just to demonstrate how we kind of put this together. We're basically looping through, in this case 500 times, and we're using that format that we just looked at. So each time it's going to put a different value in here. It's going to leak the first and the second and the third pointer off the stack. We're receiving until just because of the way that the format was. So we want to extract the address, right? So let's just try and print first of all result, and I'm going to get rid of this flag bit. Let's try and run that. So you'll see that we have all these nils in here. So whenever there was something on the stack, or whenever there wasn't anything there on the stack, we're not getting an address. So that's why we inserted this bit here to say if not nil in result. And let me just print this instead. Oops. So this is basically just printing then the actual number on the stack. So not every element is going to be printed depending whether there's actually anything there. Let me go back up here. Oh, sorry, that has the previous. Let me clear the output. Oh. Oh, we're still printing the result here. Okay, right, yeah, run it again, and yeah, so you'll see this time we don't have every element there, so any that were nil we just don't bother displaying, but now we can go and have a look and see what these elements are on the stack. But obviously we want to try and have a look to see if any of these are strings quickly without going through and manually checking for each one. And the reason we want to do that is because they mentioned in the challenge that there might be something on in the environment, so the environment variables will be somewhere on the stack. So that gets us to the final part of this. Let's uncomment this last bit of code, and all this is doing is just decoding the hex. So it needs to reverse it slightly because of the little endian format. So we're just doing that, building it all together, and we'll print it then at the end. This doesn't really work too well, but it's fine. So we'll loop through there. Let's see if we've got any interesting text here. So you can see here, Crystal, the user, we're in the home directory, so we're starting to leak our environment variables there. Let me scroll up through the stack values. You can see a lot of these aren't strings at all when we convert them, because they are actually memory addresses. But okay, that's looking pretty good. Let's try and run this against the server, and because we have this handy script here which we can just pass the remote flag into, it means I don't need to change anything at all in the script. I'm just going to go and grab this server and port number, and we're going to run it again. This time we'll pass in remote, and we'll pass in the server and the port number separated by a space. Run that. It takes a little bit longer to run. You can see it start to leak some values. I can't remember exactly whereabouts the flag might be here. I think I saw, okay, there we go, CTF. You see here CTF, and then we have our 32 byte hex value. So what we would do in this case then is just go and update our loop and say we want to run from, you know, 435 to 439, whatever, and then at the end we'll print out this flag here, which it's not going to do for us here, or it might do it, but it's just going to it's going to have everything else in there as well. The problem is if we go and specify the exact value here, the values on the stack can change, right? So every time we run it, it's going to have a slightly different value. But as long as we're able to take that and go and submit it, that's really all that matters. So we've got our first part of the flag. Let's have a look at the second part of the challenge. So the second part of the challenge says control the engine, can you take control of the engine? And you'll see that I haven't actually submitted this flag yet because I haven't solved it. But I did get it working locally, and I know, or I'm pretty sure I know what the issue is remotely. So I'm just going to go through and show how the process that I went through here, and then hopefully we'll get the flag. The phase 3 challenges are coming out tomorrow, so I don't know, it just depends how much time we get and how well the troubleshooting goes. But let's take a look here first of all anyway. So I want to talk a bit through the process here of how we would take control of the engine, because we don't have a buffer overflow to exploit here. We want to use that format string vulnerability. And to do that, first of all, I'm going to create a new project in Geardra. Let me just speed through this process a little bit. I just want to jump in here just because we can see the sections of the code a little bit easier. So we've got our functions here. We go to our main method, and we can see that how this has been compiled. It looks a little bit different to the original C code that we have here, based on the compiler. We can see our printf, which is being called here anyway, which is taking in our argument. This is where our vulnerability is. One thing we haven't discussed at the moment, and which I've only dealt with in a couple of challenges really, is using the format specifier %n to write bytes. So let me actually just bring up an article quickly, which I always kind of refer to whenever I'm reviewing the basics of format string vulnerabilities. Hopefully this can let me read it. Yep. Okay, so this basically just talks about how we can exploit these manually, a little bit about how these work. We can have a look at the format of this on the stack. Let me just try and see. We have this part here. So in printf, %n is a special case format specifier. Instead of being replaced by a function argument, %n will cause the number of characters written so far to be stored into the corresponding function argument. For example, the following code will store the integer 5 into the variable numchar. So it talks a bit here about how we can use different characters to define the length and how many characters we want to write, and how we can kind of use different values for some fine-grained control over that. But essentially this means that what we can potentially do is overwrite values within the program. So we have our got entries here. So whenever the program makes its first call to printf in the libc library, essentially what it's going to do is it's going to populate the global offset table with an address, which is going to then point to the area in libc, because that address is going to be different, and the offsets are going to be different and stuff on every system. So once that's been written essentially to the global offset table and we have an address for it, what we could do is overwrite that address in the global offset table with another address, and we could make that address point to maybe a different libc function like system. So in this case, if we were able to overwrite the got entry for printf and make it point to system instead, it would mean that we'll exploit it. It'll run through here and it'll cause some errors here, but don't worry about that. It'll cause some errors here with this printf as well. But then it's going to get to this printf again, and it's just, instead of calling printf, obviously, it's going to be calling system, and it's going to be calling system on whatever input we provide. So the input we provide could be sh or bin/bin/sh to potentially get a shell. So yeah, I just wanted to talk through that a little bit, hopefully with a bit more of a visual representation. Let's go and try and put together a script locally. So again, to save a little bit of time, I'm going to copy over some of the exploit code here, but I'm still going to run through a little bit of it just to show how I put this together. So we have a very similar script to our fuzzing script here, right? Everything up here is basically the same. The only thing that's different is some of the stuff down here. And if we have a look at the code, I'm using the format string function in Pwn Tools at the moment, but let's not worry about that too much. We have basically this format string function. It's going to identify what's the offset needed to perform write operations, which means that later on we'll be able to overwrite the got entry for printf with the entry for system that we're going to leak. So how are we going to leak this? Well, here you can see that we're trying to calculate some offsets. We've just put some question marks in here at the moment. Let's go back to our fuzzing script, and I'm going to comment some of this out again. Just comment this stuff out. I'm going to run this to 100. Take this out as well. And I'm going to run this with GDB this time. So we're going to do python fuzz GDB, and what we want to try and do is just go and have a look at some of these addresses. So typically if we're looking for a libc function, we're probably going to want some of these 7f addresses to take a look at. And actually, if we take a look at this 7f address here, 33, let's go and try and do x and then paste that in. You see that's libstart main plus 234. We could, let's have a look at the next one, 34. Okay, I need to interrupt that. Okay, so that's not actually printing, that's not pointing to a function by the looks of it. Let's have a look at 37. That's the init cache info. So we can basically go through and have a look in this fashion. You'll see we have some of these 401090s as well, which will be our local functions inside the binary. Let's have a look at this one. That was our start function. You can have a look at this, and that's start plus 42. Have a look at this one. Oh, that was the same one. So we'll basically just go through and try and work out what the offsets are in this fashion. We need to bear in mind that the offsets of the remote server can be slightly different as well. So whenever we're trying to get this, adapt this for remote later, we'd need to go through and just try and match up what we have here with what we have there. But with that out of the way, we've identified the let me just go back up to our libc start main. So we have this address. We know that this address is the 33rd element. It's pointing to libc underscore start main. So we can go back to our code and let's update this to point to 33. And that's what's going to be leaking. It's going to leak this out here. And then we want to find out what's the base address of libc, because once we've got the base address, we can then start to calculate the offsets to all the other interesting addresses. In fact, let me show a couple of different ways to do that. So we could go back to our terminal here. We have our, let me see, what was the address? This was our libc start main. Let's grab that, and then let's also do x system. And see here's our libc system. So we can do p, we're going to basically take the first address, we're going to subtract it from the second one, or we can do vice versa if it's a negative number. We can print that as hex as well if we want to. Let me do it the other way around. Okay, so that is our libc system minus the start is equal to this value. I'm going to get this the wrong way around, I'm sure, but so let's just say actually the system is equal to the leaked address minus that value. Let's see if that's correct. So I'm going to basically take this out and take out these print statements. We're going to test this out with GDB, exploit GDB. You can see we've got debug mode on there, but let's have a look. We've got a leaked address here, so I'm going to take a copy of that. I'm going to do X and paste that in. You can see that's pointing to the right place, libc start main plus 234. And let's see if we've calculated the system address properly. X system. And we haven't. That's not looking good. So I'm going to close that down, and I'm going to go back and set this to a plus instead. And I'm going to try that again. Again, we want to okay, that's, I need to add, let me just add something to the code here to stop it from exiting, hopefully. Okay, that's good. So you see we've leaked our address here, and we're going to have a look and make sure that the system address is pointing to the right place. There we go, libc system. Right, so that's looking good. So from there we can go and calculate our other offsets. We could do that in GDB as well. We can actually do that in Pwn Tools, and I will show how to do that shortly. But another way to do that would be to go and we can do LDD on, now there's a lot of ways to do this by the way, but we could do LDD on engine and see where our libc is, and then let's go and run readelf-s. You can see here it'll give us all the offsets of the functions, so we can basically just go and grep out system. You see here that the offset to system is right here, which means if we go back to our script now, we can say that the libc base is equal to system minus the 0x offset that we just saw there. And we can basically go through and say the same thing then for bin sh, for printf, etc. And that should work okay for us. What I'm going to do now is just copy over a script which I put together. Let me just take a copy of this. It's very similar. I'll show what's different about it now. Just to demonstrate as well, actually, with that fuzz script, remember the 33rd element pointed to our libc start main plus 234. So let's actually just run that against the server as well. I'm going to do python fuzz. Actually, do we still have it in here? Yeah, okay. So it was a 33rd element. We don't even have a 33rd element here, so that's not going to be much use to us. But we could take the 32nd element, and then what we can do here is go to the libc database, and we basically want to see, is that offset going to match? For us in this case, it's libc start return main. That's that libc plus 234 address that we saw. So if I enter that in here, we get no results found. So that's not, there's no libc libraries where that could be the correct value. But if we go back and have a look then, instead of the 32nd, let's try the 35th. So 2 elements behind our local system. Go to find, and this time we actually do find a pretty common libc library, and then from here we can go and work out what are the offsets, and we just basically go and update our script and just update the offsets there and try it against the remote server. So if you have it working locally, it's as simple as that. You know, make sure you leak in the correct address, find out what the offset is, what the version of libc is based on that offset, and then update all your offsets here. The reason I wanted to show my script here is because I've done things a little bit differently. So I've downloaded this libc library, and I've just set up the script so that depending on whether you pass in the remote server address or whether you just run it locally, it'll run differently. So let's have a look at this. If we run this locally, which is just the default, it's going to use our local libc library. It's going to set the stack position at 33 because that's the libc start main we want to leak. And it's basically just going to go through, it's going to leak the libc address, it's going to calculate our offsets. And I'm doing this slightly differently as well. Rather than actually just setting up variables for the libc addresses, we're actually updating our libc binary. So you see here our libc is an elf file. We're updating the address of it, which means from now on we can just reference functions in libc directly, and it'll take care of all the addresses and the offsets for us. Hopefully that makes sense. So that's why instead of the system here, instead of having addresses and things like that, we're just subtracting libc symbol addresses, libc function addresses. We can also search for strings now within the libc library, although we don't really need to grab the bin sh there. And then finally, we're just doing this format string write. So let me see, does this have any documentation? It does. So this basically is a Pwn Tools function, and it's because we've used this format string function up here, which will automate a lot of this for us. So I've got this little function here, send payload, and this will basically, it'll find the offset of the format string vulnerability, which we'll have a look at again in a second. Let me set this to debug so that you can see that. And then whenever we get down here, it's going to know how to do the write, and then we just pass in the address that we want to overwrite and the address that we want to overwrite it with, which we want to overwrite printf with system. We want to execute that write, and then once that overwrite occurs, we're going to send sh to the command line because it's going to run then system sh, or you could put in bin sh there. And then we want to hopefully drop into an interactive shell. Okay, so let's try that out. I'm going to run just first of all locally Python exploit. See, it runs through locally. Let me just scroll up here to show. This is it running through the format specifier thing at the beginning. So it's identifying, it comes back and says the offset is at 6, and you can see it's loading our libc library and stuff here. This is it performing the actual write. So this is, if we were to copy and paste, if we were to basically take all this payload code out and just send that manually, it would perform the same function. It would overwrite the global offset table with the address of our choice. So here you can see anyway, we've got command not found, which would be expected if we overwrote the printf address with system, because it'd be calling system and whatever the commands were here, this now on engine, and then this command bit, and then this bit. Not that bit again, because it's not looping that bit. So let's just try and list files and see who we are. Yeah, everything's working fine. We've got a local shell. Just to verify, I mean, if we were to overwrite that with a different address, let me go back and set that to, I don't know, instead of overwriting it with system, let's overwrite it with puts. And let me turn the debug mode off. Run that again, and you'll see now we don't have a shell. We're not getting the output because we're calling puts instead of system. So that's just verifying that that's working. We could pass this through GDB as well and go and have a look at the new address in the global offset table and stuff. But I think that's a good demonstration that's working. Let's have a look and see what the problem is now if we do this remotely. So remote, all we should need to do is just literally change this here, and we run it. No such file and directory because I don't have this libc library downloaded. 1 second. Download that libc library, which is what they should be using on the remote server. We try and run it again. And yeah, it sends everything off. It identifies our offsets here, and these offsets should be correct. Let's grab that system address, and if we go here and say, what's the offset of, what's the libc library for system, where the address is this, it should come back. Oh, it didn't come back with the same result. Okay, let's go back to the code here. One thing that I changed is we have this set to libc symbols. So it's grabbing this from the libc library now, whereas I was using the offset previously. And I guess this +234 is going to be different on each libc library. So what I'm going to do is the libc address, I'm going to instead set that to the leaked address minus, and let's go back to our library here. So libc start return. You see, I don't think I can use this. Let me just try and use this quickly in Pwn Tools. I don't think it's going to be a valid object. I don't know how just to get to the. No. Alright, so what I'm going to do is, instead of using this symbol, we'll just go here and we'll find out that the offset difference is here on this libc library, and we'll say here then that the libc address is the leaked address minus this offset, and hopefully this will work for us. Let me try that again. So it runs again. This time we get a system. It's got a different the offset at the end is different. Alright, so it's only like the last 4 digits or something, or 5 digits that'll actually, 5 characters that actually matter when it comes to the offsets here. I could just probably take the end here, but I just always just grab the address. Let's just go and try this then. Go back system and paste that address in. And you'll see actually it's come up with a couple of different possible addresses there. Let me go back, and in fact what I'm going to do, I'm going to leave it as what we had on there previously, but I'm also going to add on, so this was our leaked libc address. I'm going to put that in. The more address we have in here, presumably the more we'll be able to narrow down the possibilities, right? So, oh, where's my terminal? So there's the libc start main return, and then also we've got this system address as well. So based on those 2 addresses, it should then tell us, yeah, there's only one possibility, which was the libc library we're already looking at. So why is our exploit not working remotely then? Let's go back here and just let me put debug mode back on. just so we can see what's being sent and what's being received. Run that again, and here's the actual format string exploit. So we can see that Pwn Tools is building this. This is, let me go back to the code, this is the line right down here where we're creating this write and then we're executing the write. The problem is, and it took me a while to get this because I wasn't looking at the wrapper function at all, but the wrapper here essentially says that any input that's not ASCII letters, digits or punctuation will be rejected. So if we go back and have a look at our code here, we'll see that we actually have like FF in there, which obviously is not a printable character. So it looks like this has been designed in a way that the wrapper's being used to prevent you from using the Pwn Tools kind of auto format string exploit. So you need to go and kind of build this up a bit manually. I'm going to try and do that, but there's new challenges out tomorrow, so let's see whether we get this solved. But if not, hopefully that's provided a good kind of overview of the format string vulnerability and how we can use it to overwrite the addresses in the global offset table and return to libc, locally at least.